Hi and welcome to this Leaving Cert Higher Level Applied Maths video. This video we're looking at the 2025 Higher Level Exam Paper, question 5, part A, and this is a connected particles question. So block X and block Y are held separately at rest on a rough plane inclined at beta to the horizontal. X and Y are 1.5 meters apart. So we have some key ideas here. So they're at rest to begin with. They're on a rough plane, which means we're going to be taking friction into account. And then X and Y are 1.5 meters apart as shown. So we can see that in our diagram. So the coefficient of friction between X and the plane is a half. And the coefficient of friction between Y and the plane is 2/5. So we can label those. Coefficient of friction, we use mu. So that's mu X is a half. And then this one here, mu y is equal to 2/5. Try that better. Mu y is 2/5. So show on separate diagrams the forces acting on the blocks while they are moving. So all we need to do to get our marks here is to show them in the way that they currently are. So in this current orientation. So let's call this block X, and we just need to show all the forces acting on them. So every particle has weight. So this is a nice one to always put in. Weight is equal to mass times gravity. Now, we weren't given anything in terms of mass, so there's not a lot we can do there. We then have the reaction to the surface. Now, remember, reaction is always perpendicular to the surface. It's now going to be going out at an angle like that. So that is our reaction. And in this case, reaction does not equal to mg. It's going to be equal to a component of weight, but not the total weight. So just be careful there. In terms of movement, this X is sliding down this incline, so it's going this direction. The reason we care about the direction and the reason we always want to put this acceleration there as well, first for our force equations, but secondly, when we're doing the diagrams, it's important to know what way it's moving because friction always opposes motion. So my friction is then going to go along here. So this is my friction, and my friction is equal to mu r. Okay, so that is absolutely perfect. You've got full marks for this diagram. Now, the problem comes about when we go to work with y. Okay, so if we go and do y, same way. Okay, so let's come along and we say, right, here is weight is equal to mg. Now, I have a big issue because I now have on both diagrams that weight equals mg. And that implies that the m's are the same, which we are not told that they are. We can't make an assumption here. So although we would have got full marks for that first diagram, as soon as we get to the second diagram, it's like, well, we're saying the force is the same as the other block, which it's not necessarily. I know you might argue, but it's obviously the weight of y, but that's not how it's seen in the exams. So we need to start thinking in terms of, okay, let's call this weight x, which is mxg, and this is weight y, myg. So we do some little subscripts here. So really important. Really important that we do this, and it will save you losing your marks. So just bear that in mind. It is really important that we're not double counting any force. So then the next force we put in is reaction, and we have the exact same problem. Okay, so this we're going to have to call reaction Y and reaction X. So don't label the same force, the same letter in two diagrams unless you know it is the same. We weren't told, so we can't make that assumption. Okay, so we have an acceleration here. So that's our movement. So you can call that A, but it's not going to be the same acceleration. So let's call that B. And again, friction is going to oppose motion. So our friction is equal to mu r. But again, we need to think in terms of, okay, it's mu y times r y, which mu y is 2/5 r y. Okay, so then here we want to change those to x's. So that's going to give me a half or x. So now I have full marks on both diagrams. So please bear in mind, if we're working with multiple particles, especially in higher level where often, we don't have our information given to us, so we don't have a mass to put in. just you want to make sure that it's clearly distinguished that the weights are not the same, the reactions are not the same, the frictions are not the same. It's not enough to just say it is reaction, it is weight, it is friction. When we deal with these and have numbers, one trick I often do is write my W, my weight, equal to mass times gravity and sub in for your mass, because straight away you're then displaying that the two weights are different. That's not a big issue. However, in this case, we can't do that. So please just bear that in mind. Now, these diagrams, these are not going to be hugely helpful for us when we move forward, and they'll get us full marks in this part. But obviously, as soon as we go deeper into the question, we need to actually have all of our forces resolved. Remember that everything should be resolved parallel and perpendicular to the movement. So our movement is this direction. So we take a very good look at our diagram. We say, well, what's the issue? And it's like, well, the only one that's not either parallel or perpendicular to that is weight. So let's resolve our weight. So I'm going to move my label for weight just over here to the left. Now let me move this. So that's Wx is equal to mxg. So then when we do that, my beta is always that top angle there. If you want to see more on that, I've linked the full video below where you can kind of explore with those inclined planes, what's happening with them. But this becomes mxg cos beta, and this is mxg sine beta. If you presented this for your first answer, we just need to be careful, because have we double counted the weight? Because we have the weight plus its components, so that's like double counting it. Now mine's in a different color, but they're very similar. So what you can do just to make it a bit easier for yourself is just get rid of that extra force, so it's so clear. Okay, so that's another area where students are losing marks, where they're putting in the same force twice, because they have the force and then the resolved force. So that is double counting the force effectively. So let's take a look at this other one down here. Okay, let me just rewrite this over here. Wi is equal to myg. And again, there's my beta. So this is myg cos beta, myg sine beta, and let's get rid of that extra force there, so we're not losing any marks. So if you do want to resolve on your diagrams, bear in mind that a person correcting your work can't see when you did certain steps. So you might argue that, like when we worked through this, that I had it right and then I added in the extra forces, but somebody looking at my work doesn't know when I've added things in. So you need to make sure it's very clear. So these are the two main things we've talked about so far with regards to losing marks. You will lose marks if things are not labeled uniquely, and you will lose marks if you double count any forces. So that's including the original force and the resolved force. If it's a very clear different color, it's not an issue, but just to be extra safe, get rid of the extra force. Even for yourself, because often I see students like double counting the forces in their force equations because they don't scribble it out. Now, you might find it okay to work with this, and that's perfect. However, a lot of students struggle to get to our force equations from there. So what we can do is we can basically rotate these so that we are looking at a kind of a more familiar movement for us. So a left to right. So this is A and this is B. All I've done is rotate. So this is our X. This is a half or X. This is 2/5 or Y, and this is or Y. Now I broke out my weight into components. So then this is MXG cos beta. This is mxg sine beta. This is myg cos beta. This is myg sine beta. So they are our resolve diagrams. Now, if you presented those for part one, again, you're going to get your full marks, because everything is named uniquely and there's nothing double counted. So there's no rules on how you need to present the diagrams, as long as you're not double counting any forces and as long as all unique forces are given a unique name. Now, these might be easier for you to work with. So this format here. So if it takes you another 30 seconds to quickly redraw them so that they're working horizontally, you do that. If it helps you get the next part right, then it's worth putting in that extra time. So calculate the acceleration of each blocks in terms of beta. So I have done A and B, you could do AX and AY, whatever works. So we're going to use F equals MA, and I'm going to use these diagrams that I pulled from the last slide. So remember that our acceleration, that direction, is helping us set up where F equals MA. So for X, we start by going to the left. So that's mx g sine beta minus a half, or x, is equal to mass, which is mx times a. Now, what we can also say though is, because the way we've now set these up, we can see that forces up equal forces down. That means I can now replace my Rx with mxg cos beta. So that's mxg sine beta minus a half mxg cos beta, and that equals mxa. So our masses can be divided out. So our acceleration, A, which is AX, is going to be, we can pull out that G if you want, doesn't really matter, but we have G sine beta minus a half, or G over 2, G cos beta. And that's our acceleration of the X particle. Doing the same thing with the Y, we have myg sine beta minus 2 over 5, or y, is equal to my, and I've called that b. So again, we can see that because of the way we set this up, or y is equal to myg cos beta, forces up equal forces down. That's because we only have acceleration left and right. You can see that b acceleration is just going to the left. So we have myg sine beta minus 2/5 myg cos beta is equal to myb, and then that mass can be divided out. That gives us the acceleration for y, or b as we called it, g sine beta minus 2 over 5 g cos beta. So the only difference between our two accelerations is that coefficient of friction that's been pulled in. So we're told that the blocks collide 2 seconds after they are released, calculate beta. So that seems like quite a simple little question, but there's a lot going on. So let's set up our VUAST here for both S and T. And then let's do that for Y. V, U, A, S, and T. Okay, so we know the acceleration of both. So this is G sine beta minus a half G cos beta. And this we definitely know is 2 seconds. And this acceleration is G sine beta minus 2 over 5 G cos, G cos beta. We know they both start from rest. Now, just be careful with that SX. So how far does X travel? Well, we actually have no idea. So we can think of that in whatever way you want. I'm going to call that X. Now, how far does Y travel? Well, Y travels that X amount, plus it needs that 1.5 to catch up, because it's 1.5 behind to begin with. So that's our connection. So Sx is X and Sy is our X plus 15. So for both of these, we're going to be using S equals UT plus a half AT squared. And we're going to be working these simultaneously. So we get X equals, U is gone. So we get a half by A which is g sine beta minus half g cos beta, and then that's 2 squared. So x is going to be 2 g sine beta minus g cos beta. Okay, now we can do the same thing for y. So that's x plus 1.5. Again, u is 0, so ut is not going to impact on anything. So we have a half g sine beta minus 2 over 5 g cos beta, and then 2 squared. 2 squared by a half is 2. So x plus 1.5, that's going to give us 2 g sine beta minus 4 over 5 g cos beta. And now we're going to work with both of those equations to solve them. So that effectively gives us 2g sine beta minus g cos beta, which is my x, and I'm plugging it into there, plus 1.5 is equal to 2g sine beta minus 4 over 5 g cos beta. We have the 2g sine beta on both sides, which we can take away. And then we want to get all of our other bits together. So we get 4 over 5. And we'll go the other way, sorry. So g cos beta minus 4 over 5 g cos beta is equal to 1.5. So that's 1/5. G cos beta is equal to 1.5. Cos beta is equal to 5 times 1.5 all over g, which is 9.8. So beta is equal to cos inverse of 5 times 1.5 all over 9.8, which absolutely you can work out, but this means I only have to go to the calculator once, and that works out as 40.06, which will round to 40.1 degrees. Now, that's not a bad method, but there is a nice quick little method that I'd love to show you that is a bit shorter. Just the thinking behind it is a little bit trickier. So another method we could use to solve this that's actually nice and quick and it's worth talking about, it's using what's called relative acceleration. So all that we're saying here is like imagine x is not accelerating and since it started from rest, it's not moving. That means that if x did not accelerate, it means y would be accelerating less. So if we thought about I'll call it prime y, is just going to be a y minus ax. So that's like the new acceleration of y. So it's less of an acceleration because we're assuming x is not moving. And what that does is it gives us a nice quick little so let me set this up. It gives me a nice quick little one particle question that's going to be much easier to work with. So g cos beta minus g sine beta plus what your sine there, a half g cos beta, they're going to disappear. Half minus 2/5 is a 10. So 1 over 10 g cos beta. So that's the acceleration for y, the relative acceleration. So again, assuming that x is not moving. So then we can come along and we can set up our VUAST and we're focusing purely on y because we now have how y is moving relative to x. So imagine x was stopped. So we have 1 over 10 g cos beta. We know we have to move 1.5 meters. We know the u is 0 and we know the time is 2 seconds. So we're working with s equals ut plus a half at squared. And this is a nice, quick little way to think about it. I know it might feel like, oh, is that too complicated taking away our accelerations? But actually, in this case, it works out much nicer because the accelerations are so similar. Our relative acceleration is much easier to work with. So plus a half a g cos beta 2 squared. Got a line here. So that is gone. So that's 4, 2, so that's 1/5, 1.5 is equal to 1/5 T cos beta. Apologies. Okay, let's see. So we want to get cos beta. So let's do cos beta is equal to 5 times 1.5 all over G. And beta is going to be the cos inverse of that. Make sure your calculator is in degree mode. That gives us, it's there, 40.07 degrees, so 0.657. So that's a nice little alternative method just for simplifying the question. And there's not as many steps, there's not as much to kind of work through. It's nice. It won't always work. It works particularly well here because we're kind of dealing with, like I said, those accelerations that are quite connected.